He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Cyclones are tremendous forces of nature. They spawn only in certain parts of the ocean where they can form towering rain-laden clouds of up to 15 kilometres high with viciously strong winds. And when they hit land, as we unfortunately know all too well, they can do a lot of damage.
Fiji has seen 3 cyclones develop in its waters in a matter of weeks, with rain causing major flooding across the country.
Reports are starting to come through of the severe damage Cyclone Harold has caused in Vanuatu.
Well, as you've heard this morning, Cyclone Gabriel has cut a path of destruction across the North Island.
But they can also be a source of nutrients and life for the ocean. And this is what's captured the attention of one New Zealand researcher.
I work in several areas, mainly around coastal oceanography, but in the last 7 or 8 years I've taken an interest in the biological response from the passage of tropical cyclones in the South Pacific.
Hello and welcome to Our Changing World, ko Clerkin Cannon tēnei. Dr. Pete Russell works in the Marine Science Department at the University of Otago, and he is a storm chaser.
In the face of a giant storm that might be hiding a killer tornado, Sean realizes he may have bitten off more than he can chew.
Ronan, you need to back not that kind.
To do oceanography, you can actually sit in an office with a computer and an internet connection, which is my version of storm chasing at the moment.
It's pretty amazing the amount of ocean data freely available from both satellites and buoys. We'll get back to that a bit later for a short story about how New Zealand is doing its bit to contribute to this global network of knowledge. But first, back to Pete, who's keeping an eye out in particular for cyclones that hover and change direction. Because these are the ones that tend to produce big phytoplankton blooms that get picked up on satellites. Large splashes of colour representing life in otherwise quiet and desert-like regions of open ocean. And these blooms may be the key to helping us predict the frequency of cyclones in a warmer ocean. But let's start with how cyclones form and grow and the conditions they need. A low-pressure disturbance and some balmy water temperatures.
Cyclones only happen in the tropical ocean. You need probably surface temperatures of around 30 degrees or more, and you need that warm water going down to quite some depth. At least down to 50 metres, it should still be about 26 degrees.
This is part of why cyclones can only form in certain parts of the world.
When you get that warm ocean, hot air will rise. As that hot air rises, it cools. And then as it cools, it will start to rain. It'll release that rain. And by cooling, by going from warm, moist air to rain, the water vapour undergoes a phase change, and that'll release latent heat. So that latent heat in turn rises further. That draws in more warm, moist air from the side. That in turn cools, and it's essentially like a fire that sucks in its own fuel. And because of Coriolis, the Coriolis effect, it starts spinning, and the whole cyclone takes on a life of its own at that point. And if it stayed above warm ocean, it could just circle around indefinitely. And so it's only if they move into cool ocean that they start to lose their energy and power.
The Coriolis effect that Pete mentioned here is not only important for the formation of cyclones, it's also another factor that determines where they can form. This effect is caused by the rotation and shape of the Earth. Chubby at the equator, narrow at the poles.
On the equator, for an observer in space, you are travelling a lot faster than someone at the pole, or someone who's a metre from the South Pole's only travelling, around in a small circle, where you're doing tens of thousands of kilometres within a 24-hour period. So your east-west speed is a lot greater. It's not a force, it's an effect. So a fluid will retain its east-west speed from where it starts off from. So wind, whether it's the atmosphere moving or whether it's water moving, once it starts to move, maybe from the equator, say south, it will retain that east-west speed, and this is why it wants to move to the left in the southern hemisphere and the right in the northern hemisphere.
Basically, things can't really travel in a straight line on a spinning sphere like our planet. You can test this by trying to throw a ball straight across while you're spinning on a roundabout. So this effect causes cyclones to spin clockwise in the southern hemisphere and anti-clockwise in the northern hemisphere. And people tend to call them hurricanes or typhoons in the northern hemisphere, but they're the same. This is also the reason why cyclones don't form at or near the equator.
I explain it to my students that that's the point where Coriolis gets confused between which way it should go, because the fluid likes to move towards the left in the southern hemisphere and towards the right in the northern hemisphere. And so on the equator itself, and sort of 5 degrees north and south, you don't get these tropical cyclones because you haven't got that Coriolis that starts really spinning them up.
And while the Coriolis effect does impact big, slow-moving fluids and drives important global air and ocean currents, it does not determine what direction the water in your toilet will spin when you flush it, just in case you were wondering. Anyway, that's how cyclones are born and grow.
When it's starting to form, it's a tropical depression, then it becomes a tropical storm, then once it reaches Category 1, it's classified as a cyclone, and at that point it's given a name. So each season they have all these predefined names that have been agreed on for storms that become cyclones.
There are different scales used to rank cyclones around the world. They vary slightly, but generally they all work off the wind strength of the cyclone. In Aotearoa, Met Service uses the Australian Tropical Cyclone Intensity Scale. A Category 1 tropical cyclone will have a 10-minute mean wind speed of between 63 and 87 kilometres per hour. Category 2 goes up to 89 to 117 kilometres per hour, and so on, all the way up to Category 5, which is over 200 kilometres per hour.
Communities in WA's north are bracing for the most powerful tropical cyclone to hit in more than a decade. Ilsa is expected to slam into the coast tonight as a Category 5 system with winds of up to 285 kilometres an hour.
But when Pete is chasing storms from the safety of his office, he's not just focused on the wind strength. He's particularly interested in how the storm is moving.
The initial thing I look at is the storm track, and you can go to the Joint Typhoon Warning Centre and get their storm track data. Even on Wikipedia, if people have a look on Wikipedia, you'll see a storm track, and it's made up of these round dots called fixes, and these are 6-hourly locations of the storm, and each dot will have a different colour signifying how strong that storm is.
By looking at this storm track and with these 6-hourly fixes, Pete can work out how fast the storms are moving. And he's looking for those moving in a way that might produce a phytoplankton bloom. To explain how this works, he talked me through an example of a massive phytoplankton bloom that showed up on satellite images in the wake of one particular cyclone. Tropical Cyclone Oma.
It formed a little bit west of Vanuatu, and as it was coalescing into a cyclone, it hovered for several days in this West Vanuatu region and really started getting the ocean moving beneath it.
This clip is from RNZ's Dateline for the 19th of February 2019.
Oma is heading towards New Caledonia after lingering near Vanuatu's northern islands for 5 days. There, early assessments indicate as many as 30 houses were destroyed and extensive damage has been done to crops in the northern islands. While only a Category 2, the storm pulled 3 loops off the coast of Santo late last week, then stalled near it for much of the weekend before finally moving away.
That in turn brought up a lot of cool, nutrient-rich water to the surface. Then as soon as it moved off and the sunlight hit that water, we had a phytoplankton bloom, and this was the biggest one we've seen in the observations of ocean colour. So when we talk about ocean colour, we're talking about the chlorophyll, the amount of chlorophyll A in the surface ocean.
Phytoplankton is a catch-all term for the primary producers of the ocean. Basically, they do the equivalent job of plants on land. They use chlorophyll to capture sunlight for photosynthesis when there are nutrients available in that top layer of the ocean that sunlight can penetrate through. So satellite pictures that detect big areas of chlorophyll A on the ocean surface is a sign that something has introduced a whole bunch of nutrients and the phytoplanktons have multiplied or bloomed and are generally having a good old time. The bloom in the wake of Oma in 2019 covered an area close to 250,000 square kilometres. A particularly large bloom, due, Pete says, to the little dance that Oma did as it spawned.
Yeah, it did a sort of circular path around there, and there were a couple of right-angle bends and 180s, all within a very small space. And it spent probably about 2.5 to 3 days there. So I can look at a storm track, and if I see a group of fixes really close together, that immediately attracts my attention. And then the next thing I'll go and do is look at a sea surface temperature anomaly. And if it's quite a deep one, if the sea surface temperature is decreased by 3 degrees or more, then some good cold water has been pulled up into that region.
Again, another thing that the satellites can pick up and Pete can check out from his comfy swivel chair in his upstairs corner office. Interestingly, if the cyclone hovers in place for a long time, it will bring up a lot of cold water and actually eventually put itself out. The cold water will cause it to lose energy, similar to how cyclones do when they move into temperate zones or when they move onto land. So if the important thing for these blooms is the track the cyclone takes, then if you zoom out further, what controls that?
Changes in direction are caused by all the other big weather systems that are surrounding the storm, like highs that might be sitting over in Australia. Of course, there's always a big high over the South Pacific Gyre, so it makes it relatively easy for organisations like the Joint Typhoon Warning Centre that's run by the US Navy to predict the paths that storms potentially are going to take over the next 4 or 5 days. And the reason for this is a limited amount of space on the surface of the Earth for these big weather systems. So it's not like we're going to get hundreds in one location, okay? The type of space you need for a high example, might be the size of Australia. So the lows sort of tend to fill these gaps in between the highs because it's how warmer air can move from the tropics through to the temperate zones and the poles.
Along with a colleague, Dr. Christopher Horvat from the Department of Physics at the University of Auckland, Pete decided to delve deeper into the tropical cyclone phytoplankton blooms. So they looked at each of the 156 South Pacific tropical cyclones that had occurred since 1997 and found that 15 storms had blooms in their wake, though not at the same scale as Oma. Then they got totally nerdy about the storm track data and figured out a hover parameter for each storm. This parameter actually correlates really well with the post-storm chlorophyll A measurements.
We knew hover was a good indicator of if you're going to get a bloom and how strong that bloom would be.
This means that the hover parameter can be used to predict the likelihood of getting a bloom from storm tracks alone. But actual observed storm track data are sparse and incomplete and only cover the most recent century.
My co-author, he got a synthetic data set that goes back 10,000 years.
You confused about what synthetic data set means? Because I certainly was. I thought, is this just made up data about storms? But it's a bit more involved than that.
So a synthetic data set is a computer model data set based on real things like ocean temperature and atmospheric conditions. So a computer model produced a synthetic data set of storm tracks going back the last 10,000 years based on ocean conditions.
So with this big synthetic data set, Pete and his co-author then said, well, based on the storm tracks, on the hover parameter, how often would you expect to see these post-cyclone blooms recur in the same spot? And the answer is for any type of bloom, it's about 250 years. But for a big Oma-type bloom, it's more like 1,500 to 2,000 years. Which leads to the next question. What happens to all that phytoplankton? Like for Oma, the bloom covered the same area as the Manawatu-Whanganui region. That's a lot of green stuff.
That's what we would love to know. Does it support marine food chains? Are there things out there that can go and eat it, like little zooplankton? Then in turn they feed smaller fish, which in turn will feed larger fish all the way up to your pelagic species of fish like tuna. So do these blooms support a marine food chain? Well, that's one of the questions we'd love to ask. Some people suggest not, because the zooplankton are not there to respond to this rare sporadic event out in the offshore ocean. It's a bit like the grass grows but the cows are not there in the paddock. If that is the case, then maybe this minute marine plant material sinks down, maybe feeds bacterial food chains. But in the end, as these things die off, a lot of this stuff will fall to the bottom of the ocean as what we call marine snow.
And this leads to another interesting question. If you looked at a sediment core taken from the bottom of the ocean, would you be able to see this tropical cyclone bloom layer of marine snow? Because this could then help you estimate cyclone frequency across time.
It would be great to be able to have a good proxy for cyclone activity that goes back to the last interglacial period, about 125,000 years ago, where ocean temperatures might have been 2 degrees warmer than what they are now. So this was a field unbeknown to us when we put our paper in, but one of the reviewers pointed it to us that this is called paleotempestology, which is a relatively new field, and it mainly looks at growth rings in trees and in coral to try and tease out past tropical storm activity. But that reliably, I think, only goes back about 4,000 or 5,000 years. So, yeah, we'd like to go back 125,000 years when you had those ocean temperatures, because these are the temperatures we're expecting over the next 100, 200 years.
So chasing these past storms in sediment might help us predict what's coming for us and our Pacific Island neighbours in the future. Others are working on the future question too. Pete tells me about a paper published in 2020 that looked at recent cyclone intensity.
That looked at the number of fixes over the last 40 years across all the world and noticed that the number of fixes that are Category 3 or greater has increased in all ocean basins, I think, apart from the North Indian Basin. So from that, storms are definitely getting stronger. And it stands to reason, as ocean temperatures warm, they have to dissipate that energy in some way. So if they're getting warmer, then there's more energy to dissipate. And one of those methods of dissipation is more intense storms. I'm afraid the news is not good for particularly the Pacific Islands, but at least if they have a heads up on what to expect, it gives them the ability, hopefully, to plan.
Climate change resulting in not good news. What a surprise. For Pete, though, he's still focused on that question around whether cyclones are a source of nutrients and life. So far, we've been talking about phytoplankton blooms that happen out in the open ocean, where the hovering of the cyclone brings cold water and nutrients up to the surface. But when cyclones come close to or pass over islands, they also affect nutrient mixing in other ways. Upwelling around coastlines, interactions with coral reefs, and rain washing down the island into the sea.
The question I'd like to ask is, are tropical cyclones an integral part of supporting marine life within the Pacific Islands?
To do this, Pete is heading out to Vanuatu to work with people in fisheries there. And while that will be his main focus for now, he hopes bloom sampling and past storm chasing will also happen too.
We'll still also chase these blooms because we'd love to get a water sample from them to see what they're made up of. And of course, a bigger work would be trying to look at these sediment cores, because that would be a really good objective. That's more important for governments around the world for future planning.
Thanks to Dr. Pete Russell of the Marine Science Department of the University of Otago. If you want to read the article that Pete wrote with his collaborator Dr. Christopher Horvat, we'll include a link to it on our webpage, www.rnz.co.nz/ourchangingworld. Now, along with satellites overhead taking pictures of our oceans, there's also an extensive global network of wave buoys that others are using for their studies. In February, the Navy ship the HMNZS Canterbury was deployed to subantarctic Campbell Island for the science and conservation-focused Operation Endurance. Now, the operation was cut short because of Cyclone Gabrielle, and this was the focus of a previous Our Changing World episode called When Plans Change, which you should have a listen to if you haven't already. But before the ship returned to mainland New Zealand, it achieved one last objective. The cargo deck of the Canterbury is huge, big enough to hold massive tractor-like machinery and many, many shipping containers. And at the end of this huge space is a massive metal door. It can be lowered when the ship is at anchor to form a steep ramp from which boats can be filled and launched. But today, a small group of people have assembled to watch the deployment of a wave buoy off the back of the ramp. So the giant door is half open, even as the ship is sailing. Standing in this massive space, looking at the back, you can see waves rolling by and the occasional albatross swooping past. The buoy itself is bright yellow with black solar panels on the top and with the words scientific research printed on it in big letters. It's designed to float perfectly at the top of the ocean, and accelerometers inside measure how much it's being moved around. There's a lot of manoeuvring, heavy lifting and rope sorting to get the buoy to the end of the ramp with everything lined up and ready. But eventually, the process of deploying the buoy begins. Here's Remy Zangvogel of Calypso Science, part of the team involved in the deployment.
The sub floats went in the water first, and then the wave buoy followed, and we're watching the wave buoy going further away. And then the line will be tight, and when we'll be out tight, we'll move to position and cut the sacrificial line that holds the clamp, and the clamp will fall down to the seabed. The bat's ready. It's on the bottom.
The next day, I catch up with Dr. Peter McComb, a physical oceanographer who's working with the Defence Technology Agency and the Navy to get this job done. This wave buoy, he says, is for the Southern Ocean Waves Programme.
So that's been going since 2016, sponsored by Defence Technology and the Navy. And we are measuring waves in the Southern Ocean at the southernmost location where we can moor up a wave buoy. So we're at Campbell Island, and we're lucky that it's got some seabed that is reasonably shallow near to the island. It's around about 150 metres depth. And at that location we can moor a scientific wave buoy so that we make very precise measurements of the waves. That's all of the different wave periods and directions that occur.
And this wave buoy feeds into a wider network.
Correct. It's a civilian science program, so we share all of the data with other scientists around the world. And the data comes in real time, so it is used by some agencies, just to cross-check, what they're seeing in the weather models. But primarily, it's being used to tune the physics in the wave models that are used to both forecast and recreate historical wave conditions.
And as you say, we're quite far south, so presumably there's a bit of a gap down here in terms of wave buoys or space in the ocean where you can moor a wave buoy.
Well, it's a big, wide ocean, and the Southern Ocean goes all the way around the planet, so it does create quite a unique wave field where you have, massive long fetches where waves get generated in the Southern Indian Ocean, in fact, and travel all the way to here. Historically there was only satellites that could measure the roughness of the surface, if you like, which you recreate a wave climate from. Or in more recent years there are drifting wave buoys, but neither of those techniques provide the fidelity to get really high precision estimates of the frequency direction spectra, which is what we need.
And that wave buoy was deployed yesterday. Have you been able to check in on it?
Yeah.
Is it already transmitting?
Yeah, we got data, and there's a bunch of scientists around the world who are pretty excited right now, seeing the data come in every 3 hours. And in fact, I was looking at the data before, and we're standing on the side of the ship here looking out to sea, and we can see that sea waves are coming from one direction, and there's a big long swell coming from another one, and there's something else coming from over there. And so it's actually quite a complicated pattern of waves and the directions they're moving and interacting with each other. And that's what we're trying to capture with this buoy.
Can you tell me a little bit about the actual deployment? Because this is not, we say to deploy a wave buoy, and I kind of think, you chuck something over the side. But it was a bit more involved than that.
Well, yeah, this is the second time we've used the Canterbury for this deployment. From the Canterbury, we have a stern ramp that allows the back of the ship essentially to be opened up and creating a platform that is a couple of metres off the sea surface. And so the wave buoy itself weighs just over 200 kilos, and then we have a 220 metre cord that attaches it to, in this case, a 700 kilo anchor weight. And so there's a lot of heavy equipment to move around on the back deck, and lucky we have a really good crew, but there's good coordination required with the bridge as well. So we had the navigator on the bridge with a target zone for us to deploy the equipment. So,
because you had a specific place where you wanted the buoy to be moored, and also you needed to hit that kind of shallower zone so that it would touch bottom.
Correct, yeah. We had a target zone of around about 300 metres by 500 metres. That sounds big, but this is a big ocean we're in here, and this is quite a large ship as well. So we hit the target. And also I need to point out, this buoy is really famous because, this location, because in 2019 we recorded the largest wave in the southern hemisphere right here. It was just shy of 24 metres in individual wave heights from top to bottom. And we're kind of hoping that we'll get a 25 metre wave this year, so let's see. Yeah.
And am I right in saying that this buoy came from the Australian Navy?
Yes, an Australian research program donated the buoy for this particular program. The previous 3 deployments we used buoys from New Zealand, one from Defence Force as well. Yeah, so it's very much a collaborative science effort.
So this buoy is a replacement?
This is the 4th buoy that we've put in this area, so it's pretty hard to come back to this location. So typically we design the moorings to last for 1 year, but in one of the times we couldn't get back here for 2 years, so the buoy lasted for 18 months and then the cord broke free. The first couple of deployments we put in, we were still modifying the moorings, so they lasted around 6 or 7 months each time. One of those buoys drifted all the way across the Pacific and was recovered by the Chilean Navy and sent back to us, so we were very grateful for that. And there's actually one out there in the middle of the Pacific right now that we've deployed a couple of years ago. So, it's still collecting great data as it drifts along.
Yeah, I have to say, you looked a little nervous yesterday.
Oh, yeah, I slept well last night, that's for sure. This is always the best feeling when you're on the return leg of the voyage and you've achieved your key aims.
So that was how we left it when we stepped off the HMN's NS Canterbury. But because it's been some time, I gave Peter a quick call to see how the buoy is doing. Unfortunately, it broke free of its moorings 4 weeks ago. It's now about 100 kilometres to the east of its original position, drifting slowly. Peter says it's still transmitting valuable information that the Australian research team are using. They're looking at how swell waves decay across the Pacific Ocean, so it's still quite well positioned for that experiment at the moment. They'll keep an eye on it, and if it drifts towards Aotearoa, they'll see if they can do an opportunistic recovery. They'll have to look at putting another one back in next year, but Peter is stoic about it. It just shows you how hard won that kind of data is, he says. Between tropical cyclones in the Pacific and giant waves in the southern, we're really surrounded by some wild oceans. Thanks to Dr. Peter McComb, Managing Director of Oceanum, and Remy Zeinvogel of Calypso Science, both of whom were working with the New Zealand Defence Technology Agency and New Zealand Defence Forces to deploy the buoy. Ko Clerkin Kenana Hau te kaiho tū o tēnei hōtaka I āwhina mai at Justin Gregory, Rawa ko Ellen Rikers. I produced this episode with help from Justin and Ellen. Sound engineering was by Phil Benge, and Tim Watkin is executive producer of podcasts and series at RNZ. RNZ are producing awesome new podcasts all the time. The latest release is the second season of Justine Murray's Know My Town. Justine heads out on the road around Aotearoa to tell us the stories behind different place names. I highly recommend this series. Search for it now on your favourite podcast app, Now My Town, or find it on the RNZ website under the Podcasts and Series tab. Tēnā koe I whakarongo mai. Thanks so much for listening. Have a great week. Kia pai tō wiki.